If a single metal disappeared from the world tomorrow, your car would. Food production would collapse, and cancer treatment would be set back half a century. Yet this substance shouldn't have existed on Earth. Its birth tore space apart for light years. Great empires discarded it like garbage for centuries. And it doesn't react with anything. Not with oxygen, not with water, not with time. It simply lies in your jewelry, in your cars, in your veins, patiently waiting. Waiting for us to be gone. How the wreckage of the universe's worst catastrophe ended up in our hands. The answer begins in a dirty river 400 years ago. A Spanish soldier stands knee-deep in a dirty river. Colombia, mid-15th century. Heat under 40 degrees. Mosquitoes. Malaria wipes out a detachment every 2 weeks. Behind him is a ship filled with gold. Another jungle trek lies ahead from which half the men will not return. And so this soldier takes gray stones from the bag and irritably tosses them into the water, one after another. Heavy as lead, shiny, but not like that. Gray, irregular, trash. He calls them platinum. In Spanish, it's a diminutive silver. Little silver is a disdainful word. A name for something small and useless that gets underfoot. Now watch closely. The men were throwing overboard a substance that is worth more today than the entire cargo of their ships. More than their lives were worth by the standards of the Spanish crown. They threw it into the river with irritation because the gray stones interfered with the gold panning. They got tangled in the pans, added extra weights, stole time. But here's what they didn't know, and what school textbooks also don't tell you outright. Platinum shouldn't have existed on this planet at all. Its presence here is the result of a catastrophe of cosmic proportions. And the fact that it was located in those rivers at that particular time is a 4 billion year chain of coincidences. Let's start at the very beginning, at birth. We are taught that all elements are born in stellar cores. This is true, but not the whole truth. An ordinary star, even a very massive one, produces elements only up to iron. Iron is the limit. Its atomic number is 26. Beyond that, thermonuclear fusion in an ordinary star is no longer energetically profitable. The reaction begins to release energy rather than release it. The star can no longer burn heavier elements. It collapses. Platinum is element number 78. To create it, conditions are required that simply don't exist inside an ordinary star. A neutron density unattainable in any stellar core during normal combustion is required. An entirely different event is required. In 2017, the LG gravitational wave detectors in the United States and Virgo in Italy simultaneously detected a signal. It came from the galaxy NGC 499300, 130 million light-years away. 2 neutron stars collided there. The event was designated GW1 7817. It's important to understand what a neutron star is. It's not just a dense star. It's the corpse of a massive star that exploded as a supernova, but whose core, rather than disintegrating, collapsed under its own gravity to a state where electrons are literally compressed into protons and converted into neutrons. The resulting sphere is approximately 3 kilometers in diameter, roughly the distance from the center of Moscow to the Garden Ring, with a mass comparable to that of the Sun. The density of such an object is approximately 100 million tons per cubic centimeter. 1 teaspoon of such a substance would weigh approximately 500 million tons, roughly the weight of a large mountain range. And now, 2 such objects orbiting each other for billions of years and gradually spiraling closer due to the loss of energy to gravitational waves have finally collided. The speed at the moment of merger was approximately 100,000 kilometers per second, roughly 1/3 the speed of light. In a split second, what astrophysicists call a kilonova occurred. The total ejection of matter was thousands of times more intense than a typical supernova. Under conditions of extreme neutron density and extreme temperatures, a process of rapid neutron capture began, which physicists call the ERA process. Atomic nuclei absorb neutrons faster than they can decay through beta decay. This is how heavy elements are born: gold, platinum, iridium, and uranium. Telescopes aimed at the source GW7817 recorded a characteristic emission spectrum Scientists calculate that this single event alone produced matter with a total mass several times greater than that of the Earth. Gold and platinum are among the main products of this synthesis. All the platinum on our planet has a similar origin. Several billion years ago, long before the birth of the Sun, neutron stars collided somewhere in our galaxy. The ejected material mixed with a gas-filled cloud. This cloud later formed the solar system, and platinum settled on the young Earth along with everything else. But here's the problem. Platinum is heavy, very heavy. Its density is 21.4 grams per cubic centimeter. When the young Earth was molten, the heavy elements sank. Iron, nickel, platinum, gold, all of it sank down to the center, into the core. According to geochemists, calculations, there should be about 1,000 times more platinum in the Earth's core than in the crust. There it lies, inaccessible, at a depth of almost 3,000 kilometers. The platinum we mine is different on the way to the surface. According to the most widely accepted scientific theory, approximately 4 billion years ago, after the Earth had already formed and cooled enough to develop a solid crust, it was struck by a flood of meteorites. This period is called the Late Heavy Bombardment. The meteorites brought with them a new batch of platinum group metals, and this batch was not fully absorbed. It remained in the crust. This is what we mine. This is what the conquistadors held in their hands. This is what lies in your ring or in the catalytic converter of your car. We are literally digging through meteorite debris, the frozen spray of neutron star collisions that arrived on our planet as stone visitors from outer space. Now let's return to the conquistadors, because this story has details that most people don't know. The Spanish first encountered platinum in the area of the Rio Pinta and Rio Utrata rivers in present-day Colombia. Indigenous peoples, the Choctaw and others, had long worked with this metal. They mixed platinum grains with gold dust and heated them, not melting the platinum, but melting the gold. The liquid gold bound the solid platinum grains, and then the mass was repeatedly forged. The result was a durable composite harder than pure gold, which could be polished and turned into jewelry. In essence, they invented powder metallurgy 3,000 years before the Europeans. They didn't understand chemistry in the European sense, but empirically, through a generation of practice, they discovered a working method. The Spanish didn't understand this and didn't want to. For them, there was only one metal of value, gold. Everything else was impurities, garbage, and natural errors. In 1735, the French surveyor and naturalist Charles-Marie de Lademan took part in an expedition to measure the meridian arc in Peru. Along the way, he collected samples of interesting substances and minerals, brought platinum back to Europe, and described its properties in letters to the Paris Academy of Sciences. This was one of the first systematic European accounts of the metal. In 1748, the Spanish naval officer and scientist Antonio de Ulloa published a description of platinum in his official report on an expedition to South America. It is considered the first official scientific description of the metal in the European tradition. De Ulloa honestly wrote that the metal had long been known to the local population. He wasn't claiming to have discovered it, but was simply recording a fact. After this, platinum fell into the hands of European chemists, and that's when the real nightmare began. Alchemists and early chemists knew how to handle metals. They smelted silver, gold, copper, iron, and lead. They had bellows, forges, and crucibles. They knew how to work with fire, and they could handle all known metals. Platinum defeated them. School textbooks calmly inform us that platinum is a noble metal with a high melting point. It sounds boring. In reality, it means this. No furnace in the 15th century could even come close to the required temperature. 1768 degrees Celsius is exactly what it takes for platinum to begin to melt. A forge with bellows produced a maximum of about 1500 degrees Celsius. It was almost 300 degrees Celsius short. The platinum sat in a crucible glowing red hot, but it didn't flow. It simply sat there. Antoine Lavoisier, the man who rewrote the entire field of chemistry, established the law of conservation of mass, and created modern chemical nomenclature, was unable to melt platinum. His attempts are documented in his papers, but they were unsuccessful. In 1752, the Swedish chemist Henrik Theodor Schaefer found a clever workaround. He added arsenic to platinum powder. This lowered the melting point of the mixture. Upon subsequent heating, the arsenic evaporated. Something resembling platinum metal remained. Dirty, imprecise, with impurities, but at least it was something. The first real step. The first to obtain truly malleable, workable platinum was the French chemist François Chaban, working in Marbacca, working in Madrid at the invitation of the Spanish crown. This happened in the 1780s. His method of pressing and sintering platinum powder under high pressure was, in essence, the prototype of modern powder metallurgy. The technology was immediately classified. The Spanish crown recognized its value. King Charles II commissioned a patia, sacred vessel for communion from the new platinum, a metal that does not age, does not darken, and does not react with anything. The symbolism is obvious even without explanation. But truly pure platinum, with a full understanding of the chemistry of the process, was obtained by another man, and his story is far more interesting than that of the Spanish court. William Hite Wollaston, an English chemist and member of the Royal Society, was a man unconventional elect and an unconventional approach to the boundaries between science and commerce. In 1800, Wollaston and his colleague Smithson Tent purchased several pounds of raw platinum ore from a merchant in South America. They divided the material. Tent took the insoluble residue to study the part that didn't dissolve in acids. Wollaston took the soluble portion. With his share, Tent discovered two new elements in 1803, osmium and iridium. Both were hidden in the platinum ore, like needles in a haystack. Wollaston, with his share, also discovered two new elements, palladium and rhodium, and developed a method for producing pure malleable platinum by precipitating ammonium chloroplatinated, calcining, and pressing the powder. The method worked. The platinum he produced was excellent, pure, ductile, and suitable for precision manufacturing. And then Wollaston did something strange. He didn't publish the method at all. He began quietly selling platinum crucibles and laboratory vessels through intermediaries, without citing the source, for many years. Why? Because Wollaston realized what the Spanish crown had realized 200 years earlier. Platinum is potentially the perfect tool for counterfeiters. Its density, 21.4 grams per heap of scrap metal, is higher than that of gold with 19.3. This means that if you take a slightly smaller platinum bar, coat it with a thin layer of gold, and on the scales it will show exactly the required weight for a valid gold bar. A touchstone used by jewelers to test the metal wouldn't help either if the coating was thick enough. In a world with a gold standard, where all trade relied on trust in metallic money and bullion, the widespread adoption of this technology could collapse the European financial system. Wollaston understood this. Publishing the method meant making it available to everyone, including those who use it for purposes other than science. Towards the end of his life, in the 1820s, Wollaston began disclosing details of his method to the scientific community. He died in 1828, rich and famous. More than 20 years of monopoly on the world's finest platinum had earned him a fortune which he bequeathed to the Royal Society. The money was used to establish the Wollaston Medal, one of the highest awards in geology. It is still awarded today, and Wollaston proved correct in his concerns. Cases of gold counterfeiting using a platinum base were recorded throughout the 10th century. One documented instance occurred in France in the 1830s. Several large ingots mistaken for gold by jewelers turned out to be platinum with a thin gold plating. While Wollaston was quietly trading crucibles, something was happening on the other side of Europe that would change the very idea of measuring reality. France, 1790s. Revolution. The old order was collapsing, and with it the old system of measurement. Before the revolution, France had around 800 different units of measurement, units. Different provinces had different feet, different pounds, different pints. The same feud had different lengths in Paris and Bordeaux. Trade was a nightmare, and fraud was the norm. The revolutionary government set out to create a single, rational, universal system of measurement and one independent of the arbitrary whims of monarchs and local traditions, one based on nature. One based on nature. The meter was defined as 1/10,000,000th of a quarter of the Earth's meridian, the distance from the North Pole to the equator through Paris. Geodesists Jean-Baptiste Lambre and Pierre Michel spent several years measuring the meridian arc between Dunkirk and Barcelona to calculate this value with maximum precision. The kilogram was defined as the mass of a cubic decimeter of pure water at 4 degrees Celsius. At this temperature, water has its maximum density. And so the question arose, what should physical standards be made of? The samples that would embody these definitions in metal. A material was needed that would never change, that would not oxidize, warp, or lose a single gram over such long storage. The choice fell on platinum. The first standard meter, a flat platinum strip exactly 1 meter long, was made in 1799 and deposited in the French National Archives. It is called the Des Archives, the meter of archives. It is still kept. First standard kilogram, a platinum cylinder from 1799, is called the Des Archives kilogram. It is also kept in the archives. But by the mid-10th century, it became clear that an international system was needed. Different countries should have the same standards. In 1875, 17 countries signed the Mitre Convention and founded the International Bureau of Weights and Measures in Sèvres, near Paris. An alloy was chosen for the new international standard of the kilogram, 90% platinum, 10% iridium. Iridium was added for hardness. Pure platinum is too soft, it can be scratched with a fingernail. Iridium makes the alloy significantly harder. However, the alloy's chemical inertness remains the same as that of pure platinum. The cylinder was machined with exceptional precision. It is 3.9 centimeters high and the same in diameter. The surface is polished. It weighs exactly 1 kilogram. This piece was unofficially called the Grand Key. Since 1889, the Raton key was kept in Sèvres in a triple safe. 3 keys were held by 3 different officials. It was permitted to be removed only on special occasions for comparison with official copies. Working standards were distributed among the countries participating in the convention. Every few decades, the original and the copies were compared, and a problem was discovered. The copies varied slightly in weight. Some lost a few dozen micrograms during cleaning, while others gained weight, absorbing molecules of pollutants from the air. The discrepancies were negligible by everyday standards, but they existed. And most importantly, no one could say for sure what had changed, the original or the copies. Because by definition, the original is always right. If the big K weighs 50 micrograms less than last time, then the kilogram has become 50 micrograms lighter. By definition, because the kilogram is what it is. Well, this is a logical dead end, pure and simple. The standard cannot be wrong because it is the definition itself. But this is precisely what made the system fundamentally unreliable. In 2019, the problem was radically solved. The kilogram was redefined using Planck's constant, a fundamental physical constant of quantum mechanics that relates the energy of a quantum to the frequency of radiation. Planck's constant is fixed in 9 decimal places and does not depend on any physical object in the universe. Now the kilogram is calculated from it through a chain of equations. It is the same everywhere, whether on Earth or Mars. The big K is no longer the official kilogram. It became simply a very precise piece of metal in a triple-walled safe. But it still lies there, unchanged. After 130 years of service, there has been no corrosion or visible degradation. While governments changed, while wars were fought, while the very system of measurement was changing, the platinum-iridium cylinder lay and waited. Because waiting is the only thing platinum does best. Now let's talk about where the platinum that goes into industry comes from, because that's a whole other story, connected to specific places, specific geology, and specific people. More than 70% of the world's platinum production comes from one region of the planet, the Bushveld Igneous Complex in South Africa. Igneous means formed from solidified magma that rose from deep within the earth. 2 billion years ago, a gigantic igneous intrusion occurred here. Molten rock rose from the mantle and spread beneath the Earth's surface over an area of about 65,000 That's larger than Lithuania or Ireland. The magma cooled slowly over tens of millions of years. During the cooling process, heavier and less soluble components settled and concentrated in specific horizontal layers. This is how the famous reefs, formations rich in platinum group metals. The main one is the Merensky, named after geologist Hans Merensky, who discovered it in 1924. The average thickness of the layer ranges from a few centimeters to a meter. This thin strip in the rock cross-section stretches for hundreds of kilometers and contains more platinum than all other known deposits in the world combined. Extracting it is extremely difficult technically. Shafts extend to depths of 2.5 kilometers or more. At such depths, rock temperatures reach 40 degrees Celsius and higher. The layer is so thin that mining is required in very narrow workings. To produce 1 troy ounce of platinum, 31 grams, 8 to 10 tons of ore must be mined and processed. The entire technological cycle from rock lifting to pure metal production takes 6 to 8 months. The second most important source is Russia, but Rilska is located above the Arctic Circle. They primarily mine nickel and copper there, with platinum and platinum group metals as valuable byproducts. Norilsk deposits account for approximately 10–12% of global platinum production. The third significant source is Zimbabwe, where platinum is mined from the Great Dyke, a separate large igneous formation of similar age. Total global platinum production is approximately 180–200 tons per year. For comparison, gold is mined at around 30,300 tons, a difference of approximately 16 times. And here's an estimate cited by experts. All the platinum group metals, platinum, palladium, rhodium, osmium, iridium, and ruthenium extracted by humanity throughout history would fit into a cube with sides approximately 8 meters long. A room. Just a room. That's all we have. And a significant part of modern industrial civilization rests on all of this. The main consumer of platinum today is the automotive industry, or more precisely, catalytic converters, or every modern gasoline-powered car has a device in its exhaust system that converts toxic gases, carbon monoxide, unborn oxide, nitrogen oxides, carbon dioxide, water, and molecular nitrogen, water, and molecular nitrogen. All these reactions occur on the surface of the catalyst, coated with a thin layer of platinum, palladium, and rhodium. Literally a few grams of metal for the entire car. Without these grams, the exhaust fumes of large cities would be deadly. Not metaphorically, but literally. In 1952, more than 4,000 people died in London during the 5 days of the Great Smog. Officially, from respiratory diseases, but in fact, from air poisoning. Another 8,000 or so died in the following week from the consequences. It was this disaster that launched the clean air movement in. It was this very act that influenced the adoption of similar legislation in other countries. In the United States, the Clean Air Act was passed in 1970. Automakers were given strict emission standards. The first catalytic converters appeared on American cars in 1975. Demand for platinum soared and forever reshaped the market. The second largest industrial consumer is the chemical industry. And here it's worth stating something most people don't think about when looking at a bag of fertilizer in the store. The industrial production of nitric acid, the basis of all nitrogen fertilizers, is impossible without platinum. It uses a process developed by the German chemist Wilhelm Ostwald in the early 20th century. Ostwald won the 1909 Nobel Prize in Chemistry for his fundamental work in the field of catalysis and chemical equilibrium. In this process, ammonia is oxidized on a platinum-rhodium catalytic gauze at a temperature of approximately 800 degrees Celsius, converting it into nitrogen oxide. Nitric oxide is then converted into nitric acid, and nitric acid into nitrate fertilizers. Without these fertilizers, modern agriculture cannot feed the current population of the Earth. Demographers and agronomists estimate that without synthetic nitrogen fertilizers, the planet can sustainably feed no more than 3 to 4 billion people. Currently, there are 8 billion of us. This is not an exaggeration. This calculation has been repeatedly reproduced in the academic literature. Platinum catalysts in chemical reactors around the world literally ensure the existence of half of humanity. Oil refining. Platinum catalysts are used in the catalytic reforming process, increasing the octane number of gasoline. Without them, the quality of fuel would be fundamentally different. Fiberglass production. Platinum dyes, a device through which molten glass is forced to produce thin threads. Only platinum can withstand constant contact with molten glass at temperatures above 1200 degrees Celsius without reaction or degradation. Dentistry. Platinum-containing alloys for dental crowns and dentures. They don't react with saliva, don't oxidize, and are biologically inert. Medical equipment. Platinum electrodes in pacemakers and neurostimulators. The body doesn't attack platinum as a foreign material. It simply sits inside and does its job for years. And on top of all this, there's the jewelry industry, which most people consider the main market for platinum. In fact, it accounts for approximately 20-25% of consumption, compared to 35 to 40% for the automotive industry. Platinum ring in a jewelry store window is the tip of the iceberg. Underwater lies an industrial civilization that would begin to collapse without this metal. Now, how platinum ended up inside the human body? And this is not a metaphor. 1965, Michigan State University. Biophysicist Barnett Rosenberg is studying the effect of an electric field on living cells, specifically on E. coli bacteria, one of the standard laboratory objects. The goal is to observe how an alternating electric field affects the process of cell division. The experiment requires electrodes. Rosenberg removes the platinum ones precisely because platinum is chemically inert. The logic is clear. If the electrodes don't react with the nutrient medium, then everything that happens to the bacteria is the result of the electric field alone. A classic technique for controlling the experiment. The setup was turned on, the bacteria stopped dividing. Rosenberg checked the field, the parameters were normal. Then turned the field off, but the bacteria still didn't divide. He began methodically eliminating factors: temperature, the composition of the nutrient, medium, lighting, mechanical vibrations from the equipment. Nothing explained the result. Finally, he got to the electrodes. It turned out that platinum is not completely inert under all conditions. When exposed to electrochemical stress in the presence of chlorides in the test medium, the platinum electrode produced compounds that were released into the solution. One of these compounds inhibited cell division. It was a compound of platinum with chlorine and ammonia. Its name is cisplatin. The full chemical name is cis-diamine dichloroplatinium 2. The word cis here comes from the chemical nomenclature of isomerism. It refers to the geometry of the molecule. Two chlorine atoms and two ammonia molecules are arranged around the central platinum atom in a specific way. Both chlorines are on the same side. There is also a transomer molecule with the same formula, but the chlorines are located on opposite sides of the platinum. The transomer is biotally inactive as an anti-tumor agent. CIS works. The difference in the spatial arrangement of a few atoms determines everything. Rosenberg realized he was onto something important. The next step was testing on mice with experimental tumors. The results were convincing. Tumor growth slowed and stopped. That was 1969. Then came testing on other animals. Then came the first clinical trials on humans, which began in 1971 at several cancer centers in the United States. In 1978, the Food and Drug Administration approved cisplatin for the treatment of cancer, primarily testicular and ovarian cancer. How it works at the molecular level is worth understanding, as the mechanism is one of the most elegant in biochemistry. Cisplatin enters the cell via transporter proteins, the same ones that typically transport copper ions. Inside the cell, the chloride concentration is significantly lower than outside. Under these conditions, the chlorine atoms in the cisplatin molecule are replaced by water molecules. The molecule is activated and becomes chemically reactive. Activated cisplatin moves to DNA. There it finds guanine, one of the 4 nitrogenous bases in the genetic code, and binds to it covalently. A platinum atom can simultaneously link two adjacent guanine bases on a single DNA strand. This is called intrastrand cross-linking and is the primary mechanism of action. This cross-linking physically deforms the DNA double helix. The cell attempts to read the damaged DNA. It can't, so it tries to copy it before dividing. The process is blocked. The repair system detects the damage and attempts to repair it, but it can't cope with the platinum cross-links. The cell receives a signal of critical and irreparable damage to the genome and initiates apoptosis and organized self-destruction program. Cancer cells divide rapidly and uncontrollably. This is why they are more vulnerable to cisplatin. The more frequently a cell divides, the more often it needs to copy its DNA, and the higher the likelihood of encountering a platinum crosslink. Normal cells are also affected, especially those that divide rapidly. These include cells of the intestinal mucosa, hair follicles, and bone marrow. This leads to side effects: nausea, hair loss, and suppression of hematopoiesis. The main organ toxicity of cisplatin is renal. Platinum compounds accumulate in the renal tubules and can damage them. That's why, when administering cisplatin, patients are intensively hydrated and given large volumes of intravenous fluid to flush the compound from the kidneys as quickly as possible. Despite the side effects for a number of malignant tumors, cisplatin has been a true breakthrough. Before metastatic testicular cancer, survival rates for testicular cancer were 5 to 10%. After the introduction of cisplatin in combination with other drugs, survival rates for metastatic testicular cancer increased to 90% or more. This is one of the most impressive results in the history of oncology in the 20th century. Today, cisplatin derivatives are also used. Carboplatin, which has less renal toxicity, and oxaliplatin, which is effective against colorectal cancer. All three drugs are among the most widely used anti-cancer agents in the world. According to various estimates, more than 1 million patients receive them annually. Atoms born in the collision of neutron stars in IVs in oncology departments around the world. Rosenberg didn't plan to create drugs. He was studying the biophysics of cell division. The discovery occurred because he was attentive enough to notice an anomaly where another researcher would have written off a result as an experimental artifact. That's how real science works. Now about the future. Because platinum isn't just history, it's one of the key challenges of the next few decades. Hydrogen energy. It's not science fiction or the near future. It's already working. Hydrogen fuel cells are used in production second-generation Toyota Mirai and Hyundai Nexa cars, which are sold in Japan, Europe, and North America. Hydrogen trains from ASATM, Karatia, Aline have been running in Germany on regional routes since 2018, completely replacing diesel locomotives on certain lines. The operating principle of a proton exchange membrane fuel cell, hydrogen, is supplied to the anode, oxygen to the cathode. At the anode, the hydrogen releases electrons, creating an electric current. Hydrogen ions pass through the polymer membrane to the cathode. There, they combine with oxygen and electrons, forming water. The output is electricity and water. No carbon dioxide, no soot, no combustion engine noise. The catalyst is needed for both electrochemical reactions at the anode and cathode. The best-known catalyst for these reactions at fuel cell operating temperatures is platinum. It lowers the activation energy so much that the system operates at 80 to 100 degrees Celsius. Without platinum, either the reaction doesn't proceed at the required rate, or temperatures are required that destroy the membrane. The problem is scalability. A single fuel cell vehicle currently requires 20 to 30 grams of platinum. For comparison, the catalytic converter of a typical gasoline car contains 3 to 7 grams, several times more for a hydrogen vehicle. If hydrogen energy is scaled up to even a significant share of global transport, demand for platinum will grow dramatically. Market analysts understand this and take this into account in their forecasts. This is precisely why several research areas are being pursued in parallel. First, reducing the amount of platinum in fuel cells. Nanotechnology makes it possible to deposit platinum in a layer just a few nanometers thick. Metal consumption drops sharply while maintaining catalytic activity. Over the past 20 years, the amount of platinum per unit of fuel cell power has been reduced by approximately 10 times compared to early prototypes. Second, finding a replacement. Scientists are actively developing catalysts from more readily available materials. Iron complexes on carbon supports and transition metal alloys. Some options are showing encouraging results in the laboratory, but none yet approaches platinum in terms of the combined activity, durability, and stability under real-world fuel cell operating conditions. Third, recycling. Platinum from spent automotive catalysts and fuel cells is already being actively recovered and returned to production. According to industry estimates, approximately 30% of platinum on the market comes from secondary sources. But recycling cannot offset the growth in primary demand as hydrogen energy scales up. And here comes an idea that just 10-15 years ago was the stuff of science fiction novels. Now these are engineering challenges with specific budgets and launch dates. Resource extraction on asteroids. Metallic and stony metallic asteroids contain platinum group metals in concentrations that are extremely rare on Earth. Chondrite asteroids, rocky bodies that have not undergone the differentiation process like Earth, contain platinum in approximately the same proportions as in early protoplanetary material. Their composition is similar to that of the very meteorites that deposited platinum in the Earth's crust 4 billion years ago. Asteroid 16 Psyche is a large object in the main asteroid belt between Mars and Jupiter. According to spectroscopic observations, it has a metallic surface rich in iron and nickel with traces of precious metals. Estimates of the total value of its contents recalculated using market prices yield fantastic figures, but these numbers are meaningless because there's nothing to compare them to in the terrestrial economy. In October 2023, NASA Psyche probe departed for this asteroid. Estimated arrival time is 2029. The mission is scientific, but data on the object's composition and structure will directly determine the commercial prospects of future mining. In 2023, the California-based company Astroforge launched a small satellite to test asteroid processing technology directly in space, or space. This is the first documented commercial step toward off-world mining. The technical challenges are numerous. How to reach the asteroid with the required payload, how to secure mining equipment to an object with negligible gravity, how to crush and process the material in a vacuum and zero gravity, how to return the mined material to Earth or use it in space. Each of these tasks is at the level of a lunar program, or more complex, but the economic logic is unambiguous. If hydrogen energy scales up as the energy strategies of most major industrialized countries are moving toward, demand for platinum will grow so much that off-world mining will become profitable even at the current cost of space launches. This isn't a matter of space exploration dreams. It's a matter of arithmetic. The platinum that Spanish soldiers tossed into Colombian rivers could become the very resource that makes off-world industry economically inevitable. Unromanticism, greed, scarcity, necessity. Now the final point, the reason all this was worth telling from the start. Consider the path we've traveled. A metal born in the collision of neutron stars billions of years before the sun, fallen to the young Earth in meteorites, found in Colombian rivers by indigenous peoples who knew how to work with it, thrown into the water by Spanish soldiers like garbage, defeating all alchemists and early chemists with its stubborn refractoriness. It became the secret commodity of an English scientist who understood the dangers of this knowledge, formed the universal system of measurement, and accidentally became a cancer cure in the hands of a biophysicist who was studying something completely different. It became the supporting structure of an industrial civilization, unsuspected by most of its inhabitants. And now, the potential reasons for humanity's first truly economically motivated leap beyond its planet. One element, 78 protons in the nucleus. Atomic mass 195.8. Melting point 1768 degrees Celsius. There is a concept called entropy. The second law of thermodynamics says, everything tends toward disorder. Everything collapses. Iron rusts, wood rots, Stones crumble over geological epochs. Mountains smooth out. Even gold dissolves in a sufficiently concentrated mixture of hydrochloric and nitric acids in the so-called aqua regia. Everything obeys this law. Platinum, too. Under extreme conditions, the same aqua regia, concentrated and hot molten, alkalize at high temperatures. Platinum gives in. Physics is honest here, too, but in real-world conditions, in air, in water, in the ground, in the human body, on the ocean floor, platinum behaves as if the second law of thermodynamics was written for it. A platinum ring thrown into seawater today will lie on the bottom in a million years the same as it was on the day it was made. Geological processes will raise and lower the seabed several times. Sedimentary rocks will cover it and uncover it again, and the ring will lie, without corrosion, without change. This is not a metaphor, it's chemistry. We humans live on average 70, 80 years. Civilizations exist for thousands of years, the most resilient ones. Our most durable structures last several thousand years under favorable conditions, then collapse. We fight entropy with all available means: medicine, architecture, writing, digital memory. We want to leave a mark. Look. Now look at the platinum iridium cylinder in the basement in Sivra. It was a kilogram for 130 years. It saw, metaphorically, 2 world wars, the collapse of empires, the advent of nuclear weapons, the space age, the digital revolution. It hasn't changed. The people who created it are long dead. The countries that signed the metric convention have changed beyond recognition or disappeared. The measurement system itself has changed. The cylinder? No. Rosenberg accidentally killed bacteria with platinum electrodes, and this ultimately gave millions of cancer patients a chance of survival. Spanish soldiers threw platinum into rivers, and now engineers calculate orbits to asteroids for its sake. Each generation has looked at this gray metal and seen something different. Trash, a riddle, a key, a cure, a foundation, a future. But here's the point. Platinum doesn't know it's important. It knows nothing about conquistadors or the kilogram or cancer or hydrogen. It just exists. 78 protons, electrons in orbit, a crystal lattice, chemical bonds too strong for oxygen and water. Everything. And we build civilizations around it, fight wars, geek, invent fly into space. We call it noble. But nobility is our term. Our admiration for something that doesn't concern us at all. Platinum was here before us, in the form of fragments of dead stars flying through empty space for billions of years. It will be here after us in the form of the same atoms, scattered across the same or other corners of the universe. Mountains will rise and smooth out. Oceans will evaporate when the sun swells into a red giant in 5 billion years. Earth will be swallowed up or thrown into a new orbit, and the platinum atoms will continue on their way. They remember nothing of us. They will never remember anything. Does that scare you? Or does it calm you a little? Because there's another way to look at this story. We are creatures who live for 70 years on a small planet in an ordinary corner of an ordinary galaxy. And we were able to figure out where platinum comes from. We calculated that it is created in the collision of neutron stars and confirmed this with real-time observation in 2017. We used its atoms to defeat cancer. We trusted it to define the kilogram. We build devices from it that convert hydrogen into electricity without emitting a single gram. That's not so little for temporary residents. But temporary, that's for sure. Platinum will remain. We will not. And that's the only thing she would tell us, if she could. Coldly, without malice, without sympathy. Simply as a fact of chemistry and physics. 78 protons, 1768 degrees to melting,